This lecture is about static equilibrium. Static equilibrium means that an object is not moving and it's not rotating. So the conditions for static equilibrium are that the acceleration equals 0 and alpha, the angular acceleration, also equals 0. From that, it follows that the sum of the forces in the x direction have to equal 0 for the object not to move side to side. The sum of the forces in the y direction have to equal 0 for that object to not move up and down, and the sum of the torques have to equal 0 for that object not to rotate. In order to solve problems for objects in static equilibrium, we're first going to draw a force diagram for that object. You're usually going to want to put your axis on your unknown force. We'll see why in a little bit. Then you're going to write these three equilibrium equations. The sum of the forces in the x equals 0, sum of the forces in the y equals 0, sum of the torques equals 0, and you're going to use these equations to solve for any missing information. Here's our first example. An 8-meter long seesaw of mass 20 kilograms has its fulcrum located 3 meters from its left end. A 40-kilogram child sits on the left extreme end of the seesaw, and a child of unknown mass sits 1 meter away from the right extreme end. First, we want to draw a free body diagram for this seesaw. So, starting over from the left end, looking at all of the forces that would be acting on this system, first we have weight from this person here on the left. I'm going to call that FG1. We have some other objects that have weight here. Definitely this other person. I'm going to call that FG2. And there is a weight from the seesaw itself. Since the seesaw has mass of 20 kilograms, it's going to have weight. And we're going to pretend that all of the weight of that seesaw can be located right in the center of the seesaw. So we'll put that right here. And I'll just call that FG seesaw for now. And there's one other force. The force would be the normal force from this fulcrum pushing back up. So I'm going to label these distances. This would be 3 meters. The seesaw is, the weight of the seesaw is halfway, so that's going to be at 4 meters. And then this other person is here at 7 meters, and the whole thing is 8 meters. And we want to find in part B the mass of the second child. So in order to find our unknowns here, we need to use our conditions for equilibrium, which say that the sum of the forces in the x direction have to equal 0, sum of the forces in the y have to equal 0, and the sum of the torques have to equal 0. Here, the system isn't moving right and left at all, so I'm not really going to care about the sum of the forces in the x direction. For the y direction, let's see if I can just use the sum of the forces in the y equals 0 and solve for the mass of the second child. So in the y direction, I have negative FG1. I have a positive normal force minus the weight of the seesaw minus FG2. And that equals 0 because the seesaw is not going to be moving up and down. Let's see what we know here. The first guy has a mass of 40. Normal force, I don't know. Seesaw has a mass of 20. And I'm looking for this mass of my unknown child. So I look at this equation and I go, this is not going to help me quite yet because I have 2 unknowns. Good thing is we have other equilibrium equations that we need to satisfy. So I'm going to leave the y part alone for now, and I'm going to look at my third equation for equilibrium, that the sum of the torques have to equal 0. So I'm going to add up all the torques here and make sure that they sum to 0. I'm going to put my axis on one of my unknown forces. That way, if my axis is on that unknown force, it's not going to need to be included in my torque equation because that radius or that lever arm distance will be 0, and it's going to make this problem easier to solve. So here, I'm going to put my axis right on my fulcrum. Makes sense to do that. So let's draw right here. That is going to be my axis. And I'm going to add up all my torque. So on the left-hand side, I have FG1, 3 meters away. And since that torque is going to cause this thing to move counterclockwise, I'm going to make that negative. Then on the other side of the fulcrum, I have the force pulling down from the seesaw, a distance of 1 meter away. That's going to cause this thing to rotate in a clockwise direction, so it's positive. And then I also have FG2. That's a distance of 4 away. Sorry, that got sort of squished. Let's try and fix that. FG times 4. There we go. And that is all going to add up to 0. We'll plug in here. Negative 40 times 9.8 times 3 plus 20 times 9.8 times 1 plus M2 times 9.8 times 4 equals 0. What do you know? Since I put my axis on my fulcrum, the only unknown here is M2. M2 is 25 kilograms. So you may have noticed that I could have just used the torque equation without writing my sum of the forces in the y direction. The torque equation would have given me the answer to part B. What is the mass of the second child? However, I didn't really know that looking at this problem from the beginning. And if we now go on to part C, it asks us what is the normal force supplied by the fulcrum. I've done all the work now. All I have to do is plug M2 back into my Newton's equation in the y direction. And when you solve for the normal force supplied by the fulcrum, you get 833 newtons. Our next example problem says that a 10-meter long uniform ladder weighing 400 newtons rests against a frictionless wall. The ladder makes a 50-degree angle with the horizontal, and a 750 Newton painter is 3/4 of the way up the ladder. And there's a whole lot of things we want to find out about this. The first thing we need to do is draw a free body diagram of the ladder. Keep in mind this ladder is not moving at all. It is in static equilibrium, so the sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, and the sum of the torques are going to equal 0. So if we draw the forces, I'm just going to start, we'll start at the top of the ladder and work our way down. At the top, this ladder feels the wall pushing out on it, so I'm going to call that here normal force. We have a 750 Newton painter 3/4 of the way up the ladder, so somewhere here I have a force of 750 newtons pointing down. The ladder itself weighs 400 newtons, and the weight of the ladder is going to, we can pretend that that's located right at the ladder's center. So here we have a 400 Newton force. And then if we go down to the bottom, the ladder at the bottom is going to feel two different forces. It's going to feel the ground pushing up on it. I'm going to call this F sub y just because we already have a normal force here, and I don't want to get confused between those two because they're different. And if this ladder was on like a completely frictionless surface, it would want to slide out. So we also have a friction force right here that's keeping this ladder, helping keep this ladder in static equilibrium by acting between the ladder and the ground. So those are the forces. I'm going to add in some distances here. So this 400 Newton force rather is at 5 meters. This is at 7.5 meters. And the whole ladder is 10 meters. So we've drawn our free body diagram. Part B says, what is the force that the wall exerts on the ladder? So in order to solve these problems, I'm going to need to use my conditions for equilibrium, which say that the sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, and that the sum of the torques equals 0. So what is the force that the wall exerts on the ladder? That is asking us for the normal force up at the top there. So we're ultimately going to need to write all of our equations anyway. The x equilibrium equation, the y equilibrium equation, and the torque one. You don't necessarily need to know which one to start with. You're going to need them all. But we're going to start with the torque one this time. So let's write our equilibrium equation for torque, which says the sum of the torques equals 0. So we're going to look at the torque created by each of these forces, add them together, that has to equal 0. I'm going to set my axis right here in the bottom left because there's two forces there. So since the lever arm will be 0 for both of those, I'm just going to have two less forces in my torque equation, so it's going to make this easiest to solve. So looking here, we need to look at each force times its lever arm distance, or the FR sine theta, if you remember that from yesterday's lecture. Really what we're doing is we need to pick out the part of the distance that is perpendicular to the force. Again, we need to look at these forces. We need to look at the distance from the force to our axis, but only the part of the distance that is perpendicular to that force has any effect on the torque. So I'm going to do that now separately so that we don't have all kinds of, get a really long equation basically that's kind of confusing to solve. So I'm going to look at what these distances would be. If I come out here to my 400 Newton force, the real distance to the axis is this. However, only the part of that pink line that's perpendicular to my 400 Newton force creates any torque. That would be this distance here. I'm going to call that distance A. That's the perpendicular part of that distance, or the part that's perpendicular to the 400 Newton force. In the same way, the part of that whole distance that's perpendicular to my 750 Newton force is this part right here, which I'm going to call B. And my normal force points horizontally. That means that the part of the distance that's going to be perpendicular is actually this distance right here, which I'm going to call C. And I'm going to represent these distances using what I know about geometry. So that distance A, I can represent as 5 times the angle, the ladder makes an angle, it tells us, of 50 degrees with the horizontal right there at the bottom. So that distance A would be 5 cosine 50, or 3.2 meters. Distance B would be 7.5 cosine 50, which is 4.8 meters. Distance C would be 10 sine 50. Okay, distance C is also this distance right here. That's the opposite side of that large triangle, or 7.7 meters. Now that I have these distances, I'm going to use them to write my torque equation. So the sum of the torques equals 0. I'm going to start from my axis and move out. The first force that I hit is my 400 Newton force. The perpendicular part of the distance is A. That force is going to cause this thing to rotate in a clockwise direction, so it's positive. 750 Newton force with a lever arm distance of B, also positive. And then I have my normal force at a distance of C, which if I pulled on with this force, it would cause this thing to rotate in a counterclockwise direction, so it's negative. Plugging in the distances for A, B, and C. My only unknown is the normal force. And I can solve and find that my normal force is equal to, I believe, about 640 newtons. So I've done part B. What is the force that the wall exerts on the ladder? I knew I had to use the torque equation there. If you tried to use the x direction, for example, or the y direction, you would have just found that you have too many unknowns, and eventually you would get to the torque equation and realize that that helps you solve this. So that was part A. Let's look at that was part B. Let's look at part C. What is the y component of the force that the ground exerts on the ladder? That is asking us for our F sub y. Okay, so this is a y direction force. I already did my torque equation. Why not use my equilibrium condition in the y direction? Sum of the forces in the y direction has to equal 0. In the y direction, I have that F sub y force. I have 400. I have 750, both pointing down. This ladder is not moving up and down. Therefore, that y component of the force that the ladder exerts on, or that the ground exerts back on the ladder, 1,150 newtons. Part D, what is the x component of the force that the ground exerts on the ladder? That is my friction force. Let's solve our equilibrium condition in the x direction. In the x direction, I have that friction force, and then I have the normal force up at the top. That's it. I already solved for my normal force, the torque equation in part B, so the friction force is also equal to 640 newtons, so that this thing doesn't slide forward and backward. Lastly, in part E, if the ladder is on the verge of slipping in its current condition, what is the coefficient of static friction between the ladder and the ground? Here, we have to remember that the friction force is equal to mu times the normal force. In this case, the normal force that is important in creating that friction is that F sub y normal force. The friction force I found is 640 newtons. Mu F sub y is 1150. I already found that. Therefore, the coefficient of friction is about 0.56. This last problem we are going to do together in class, so please just read through it. You can try it yourself, and we will review it in class tomorrow.